time we were in the midst of doing the legwork to get the structure of the proof that differential equations have solutions. And what was the first ingredient? The first ingredient was, well, derivatives, differential operators have the annoying property that they tend to make functions less nice. If you start with a function that's 5 times differentiable and take the derivative, well, now you have a function that's 4 times differentiable. You start with a function that's differentiable and you take a derivative, well, you have a continuous function. So that's the wrong. You don't want to use derivatives to define the operator to study this, unless you want to say only study infinitely differentiable operators or something. Which, I mean, one could. So instead, if you take differentiation and rewrite it, you get integration. And integration is an operator that tends to take functions and make them nicer. If you start with a bounded function, you get a continuous function. Start with a continuous function, you'll get a differentiable function. So we'll study this operator, the operator given by integrating against the function, defining the operator that function. And if that has a fixed point, then that fixed point solves the differential equation. And you can Borsky that. So in order to prove that that operator has a fixed point, we need two things. Well, we need one thing. We need it to be a contraction mapping. But before we can show it's a contraction mapping, well, it's a contraction mapping when regarded as a function defined on what space. And so in order to do that, we proved lemma 2. So I'm going to write down a list of numbered assumptions. Let's see, F. We'll start with the continuous operator. You have x0 in AB, y0 in CD. L is the max. So if you like, it's the radius of that interval where you think of the center of the interval being this point x0, even though it's not actually the center. Set m0 to be the supremum of what? Let's follow the way to write it. This is the right way to write it. No, that's the right way to write it. Where A and B. No, that should be X and Y. Then the operator T sends, well, no. Assumption's false. So there will be assumption, I guess, 0, 1, 2, 3, 4. And d2 of f of x, y, absolute value varies, is less than or equal to some parameter that we call that 1. So there are the assumptions between lemmas 2, lemma 2, and lemma 3. So what did lemma 1 say? It says that under conditions 1 through 3, T sends the set of continuous functions defined on AB to CD to the set of continuous functions from AB to y0 minus m0l, y0 plus m0l. And so if we hope it to be a contraction mapping, then we need that sort of containment, just in order to have the domains line up so that we can even check if it's a contraction. Lemma 2 says that under assumptions 1 through 4, the distance from t of phi to t of psi is less than or equal to a number times the distance between p and psi. And what was that number?
L times M1.
Cool. So this is like everything we need to prove that. Did we actually finish the proof that t is a contraction last time? Yeah, okay. Well, these two kind of already do it, right? If we can get this to be contained in that, then t maps a set to itself. If this number is less than 1, then t is a contraction mapping. So there is corollary 4. Corollary 5? Oh, no, we didn't quite finish proving lemma 3. Okay. C. Well, we finished enough of it to know how the rest of the proof will go. So now we even know what the lemma says. So based on how last time went, would people like to finish writing all the words in this? Okay, then we will do. So how did it go last time? So if S is, we set S to be D sup. So for every x in AB, the difference between phi of x and psi of x is less than or equal to that sup distance. It's less than or equal to S. And now that we know what goes in the blank, we can see that we want to show that D sup from t of phi to t of psi is less than or equal to L times M1 times S. And in order to do that, well, if you want to compute D sup from t of phi to t of psi, well, that means we want to compute the distance from t of phi of x to t of psi of x, where that t of phi of x doesn't mean function composition. T of phi is a function, which then eats that x. Oh, this is zoomed incorrectly? There. Okay, so we just need to compute this difference for every x value. So the difference for distance from t of phi of x to t of psi of x, well, there it is after some simplification. Integrals are linear, so I can take those two integrals and just subtract the integrand. That integrand, so this is where we'll pick up on the next page, but let's remember the overview. That's the function big F evaluated at two different inputs, but the two different inputs only differ in their second coordinate. And this is exactly the situation Gesundheit, where we can apply the multivariable mean value theorem. We can conclude that that difference is the same as the derivative of f with respect to the second variable, evaluated at t, comma, something between p of t and psi of t, which I guess, at least in this green line, is called q of t. I think I decided that because that's what I call it in the notes on the next page. And there's p of t minus psi of t. I know it's just broad stroke stuff. Do we have an upper bound on the length of that interval? I think it's that L, I guess. Do I have an upper bound on how big d2 of f is at every input? It's that. I have an upper bound on that. It's s. So there's the structure of the proof, but let's maybe just write those words said out loud. We can say them. Blah, blah, blah. They have the different inputs only in their second coordinate. So we can appeal to the multivariable mean value theorem and see that there is some q. Well, you know what I'm about to write because it's written in green on the last page, right? That this difference is equal to d2f evaluated at t, comma, q of t. Therefore, well, this difference is equal to the integral from x0 up to x of d2f evaluated at t, comma, q of t, all that multiplied by phi of t. Ooh, nope. Right? That's what the mean value theorem actually says. It says that the average rate of change should agree with the derivative, not the difference literally agrees with the instantaneous rate of change. That would be silly. So now we can just write things out. By assumption, this quantity is less than or equal to m1. That quantity, even in absolute value, is less than or equal to s. And the length of the interval from x0 to x is at most l. So this thing is less than or equal to the length of that interval, L, times the upper bound on D2F. Oh, I missed my absolute value pairs there. L times M1 times S, also known as L times M1 times D sup from phi to psi. Oh, cool. So what does that mean? That means that this quantity is an upper bound on something. It's an upper bound on all of these, no matter what x is. Since it's an upper bound, it's bigger than or equal to the supremum of all of those things. And what's the name for the supremum of all of those things? I'm going to write down a thing, and you'll tell me what it is the definition of. But I guess in this case it's a G comma H. So that means if I replace that G with a T phi and that H with a T psi, so tell me again, what is the least upper bound for the set of all things that look like that? Yeah. So the actual least upper bound is less than or equal to that. L times M1 times D sup of phi comma psi. Nice. Cool. I mean, that proof was straightforward once we already knew how it went from last time, right? So we need T to be a contraction mapping. So look at so there's the result of lemma 2. So what inequality do I need to be true if I want T to be a contraction mapping?
Would the bottom have to be less than 1
Yeah.
or greater than 0?
Yeah, this quantity in particular needs to be less than 1 and bigger than 0. It's already bigger than 0 because I think M1 was an upper bound on an absolute value of a function. This L is a max between two positive things, so it's positive. So we just need it to be less than 1. We need the quantity L times M1 to be less than 1. And we could solve that for L, but I think I'm not going to use that anyhow. Now we know everything. We need to pick all of these variables, all of these parameters, so that this is contained in that. And so that this is less than 1. Putting all those together, here is the corollary we get. Fix some x0 and y0 in R. So those are the same x0 and y0 that are showing up in the IVD. Fix some positive numbers, length x and length y. Let's set A to be x0 minus Lx, B to be x0 plus Lx, C and D to be the same thing but for y's. Let's assume the following. F from A. The function f is continuous on the rectangle that we need it to be. M0 is the supremum of all of the function values. D2f is defined and bounded above an absolute value by some M1. And Lx times m1 is less than 1. Lx times m0 is less than or equal to Ly. I claim then that it follows pretty quickly that the operator T sends C, A, B, C, D to the set of continuous functions that from the interval A, B to the interval C, D. And it's a contraction. And, well, you know how we're going to do it. It sends this to that because of lemma 1. And it's a contraction because of lemma 2. So let's just see that that actually is going to walk out. Was it lemma 2 and lemma 3? Is my numbering off on the board? Okay, well, that's okay. Now is my numbering correct? Okay. Unfortunately, on a chalkboard, you can't use /ref. Not that I don't screw that up anyway. So, let's see. So lemma 2 says that T maps C of AB, comma CD to something. It says it sends it to C of AB, comma y0 minus m0l, y0 plus m0l, where L is the max between those two things. So maybe we'll start by computing that. That's why I have these lines below for like some scratch work. We'll figure out what goes in the blank. So let's see. L is going to be the max between x0 minus a and b minus y0. What is a? As stated in the lemma?
x0 minus L sub x.
X0 minus L sub x. So what is this?
L sub x.
What's that?
L sub x.
So what's the max?
L sub x.
Cool. So the next thing we see is it looks like we care what this m0 times L is. Oh no, this is actually just all we need. Okay, so y0 minus m0L x to y0 plus m0 Lx. And I need to convince myself that that is contained in the interval from C to D. Let's see, what facts, what thing do I get to, do I assume in the theorem statement, corollary statement about m0Lx?
It's less than L sub y.
Yeah. So let's do that. Well, m0Lx is less than or equal to Ly by assumption. And let's see, if I want to show this is the big O interval, then I want C to be like the littlest of all four of those things. So let's start with C. So C, what is C set to be in the statement of the corollary?
Y sub 0 minus L sub y.
Y0 minus L sub y. Using the thing that you just told me is true by assumption, what inequality do we get? So I can replace that Ly with m0 times Lx, and I'll be subtracting a little r thing, so it will get bigger. Oh, I wrote them in the wrong order. That's okay. And that's strictly less than y0 plus m0 Lx, because both of these things are positive. And I guess you know what should go on the other side. What do you think the next thing that should go in that string of inequalities is?
Y0 plus Ly.
Y0 plus Ly, because what is that equal to? Cool. So, I guess I was supposed to go over multiple lines, but it fits. So that, I claim, means that the set of continuous functions from AB to y0 minus m0 lx to y0 plus m0 lx is contained in the set of continuous functions from the interval from a to b to the interval from c to d. And informally, why should that be true?
Because of the containment we just proved.
Yeah, somehow that should basically be it. Maybe we'll do it like super formally. How do you prove a set containment?
First shows in the second.
Pick a thing in the first, show it's in the second. So let's let phi from AB to y0 minus m0 lx to y0 plus m0 lx be continuous. I.e., phi is in, well, I don't want to write the whole thing, so let's be like sloppy. I.e., phi is in that set star. So I guess the real move would be to like preface this by saying let x be the thing that's called star up there. Okay, and I need to show that phi is a continuous map from the interval AB to CD. Is phi continuous? So all I need to show is that it maps AB to CD. So let's see, for any x in AB, phi of x is in y0 minus m0 lx to y0 plus m0 lx. That's what it means to be a function from one thing to another thing. And what do I know about that thing that phi lives in?
It's contained in CD.
It's contained in CD. So phi sends AB to CD. Groovy. Everybody happy? So this now verifies that T sends the interval from A, sends a set of continuous functions from the interval AB to the interval CD, to the set of continuous functions from the interval AB to the interval CD. Happy enough? And that's just like, that was a lot of words, but that was all basically just like, pick the variables in level 1 that give us the Okay, so now let's fix some phi and psi. So now I need to show that it's like a contraction mapping. And this will be even easier. So pick any phi and psi in the interval from CAB to CD. By lemma 3? Lemma 3. What can you tell me about d sup t of phi to t of psi? So let's consider any phi and psi in C of AB. What do I know? Let's see, do I have all of the assumptions of lemma 3 in the statement of the corollary? Yeah, so I can appeal to it. So let's see, by lemma 3, d sup from t of phi to t of psi is less than or equal to less than or equal to what?
LX, because we said L is equal to LX.
Yeah, so in the statement of the lemma it's called L, but now I want an LX and an LY. So it's LX times d sup phi comma psi. Ah, yes. Yes, I do. Sorry, that sounded annoyed at you, but it was annoyed at me. I need to figure out where I erase some pens so it's less problematic. Okay, good. So what was my goal? My goal was that d sup t phi t psi is less than a constant times d sup phi psi. Have I just done that? Do I know something about that constant? It's less than 1 by one of the assumptions of the corollary. M1 times Lx. Maybe I'll even add clarity by saying C, which I will set to be equal to that, is in 0, 1 by assumption. So does that mean T is a contraction? That's all the corollary claimed. We proved something about contraction mappings, and that thing about contraction mappings is why we're even considering this operator on fixed points. Nope. What's true about contraction mappings? They're fixed points. And if you trust my ability to keep my references straight, that should be Theorem 11 from Notepad 19. We showed that a contraction mapping has, not even fixed points, has a unique fixed point. Fixed is spelled with a D, point. And let's call that F. Wait, so every contraction mapping has a unique fixed point. So in particular, corollary 5 says what about the operator T? It has a unique fixed point. So by corollary 5, T has a unique fixed point. And now I'll call it F because it should be a function. Combining that observation with proposition 1, we get the following theorem, the current Lindelof theorem on the existence of solutions to initial value problems. So here's the statement. Fix some initial conditions, x0 and y0, in the real line. Fix some positive quantities, Lx and Ly. Set A, B, C, and D to be as in the corollary. Assume the following, and these are the assumptions in the corollary. You can go ahead and double check by flipping back if you want. Then the conclusion is there is a unique function defined on the closed interval from A to B to R, which solves this initial value problem. Okay, well, apparently the first thing I want to do is appeal to corollary 5. What does corollary 5 conclude?
T is a unique fixed point.
Wow. That's what it implies, I guess. But what does it actually say? It's a contraction. Yes, right here it says it implies that it has a unique fixed point. So that's a fair. And moreover, T maps C of AB to C D to C from A B to C D. That is a contraction. Hey, it's a contraction mapping. Okay, so that's written twice now. The Theorem 11, which is apparently correct because no one corrected me saying that reference is wrong at this point, now concludes, as Shane pointed out, that there is a unique, and notice that's in bold, fixed point F in the set of continuous functions from CAB to CD. What does proposition 1 conclude? What does proposition 1 say?
A function F solves the IVP if and only if F is a fixed point.
So we certainly have F as a fixed point, so that means it solves the IVP. So that definitely achieves existence of a solution. Uniqueness maybe matters less. Let's talk about uniqueness. So suppose there were two different solutions to this IVP. And both of those solutions would have to be fixed points for t. But how many fixed points does t have? Just the one. So they have to be the same. So it is actually a unique. Just because this word unique is there. Over the interval AB. And so that completes the proof. The homework assigned for today, at least a big chunk of it, and last time, was using that to deduce the existence of a natural exponential function, which I guess you've already done by deducing the existence of a natural logarithm and then importing it. But another way you can define the natural logarithm, well, so what's the important property that e to the x is supposed to have?
Derivative. Yeah.
It's its own derivative. It solves IVP. It solves the differential equation f prime is equal to f, and I guess e to the 0 is 1. So, I bet you could use this theorem to prove that such a function exists. And then you would just say e to the x is by definition that function. So, let's go ahead and use it right now to prove that that initial value problem has a unique solution, at least over some small interval. And generally, you don't expect IVPs to have solutions that are defined over the whole real line. This one does, though. The easiest argument might not do it. Well, let's do some scratch walk just to figure out how to appeal to the theorem. Let's see. Since Dan wasn't here, I still have Dan's copy of the notes. So there's the statement of the theorem. So if you want to prove that that initial value problem has a solution, what do you think I should take big F to be? So this deduces the existence of solutions to differential equations from f prime is equal to big F of x comma f of x. Is that something that depends on f comma f of x?
Yes.
Yeah, so I guess this is scratch walk, so I maybe don't need to include all the words. Let's set big F of x comma y to be what? Sine of x times y. Yeah, that'll do the trick.
Does it matter if we use f of x or y in the notation?
I think I'd want to use y right now because I want to emphasize that, right, big F is just a function of two variables. The parameter y doesn't have to be f.
Okay.
I mean, I guess you could say big F of x comma little f is that. But I would be unhappy if you said big F of x comma f of x.
Okay.
Because then it sounds like, oh, the only thing you can have in that second parameter is a function.
Gotcha. Okay.
Yeah. But I'm going to use y. I mean, it's the second argument in a function. It should be y. So let's see, what other things? So let's just go through some of the things that we need this function to be. What things do I need this function to satisfy to appeal to the Parrot-Lindelof theorem? It needs to be continuous. Over what subset of R2 is that function continuous? Over what's the maximum subset of R2 containing the origin on which that function is continuous? Sorry, the biggest rectangle. It has to be a rectangle. This statement has to do with rectangle. What's the biggest rectangle?
Well, you know, y is going to be between 0 and 1.
Okay, but I just want kind of continuity. Let's not deal with all of the parameters at once. It's everywhere, right?
Oh, isn't
Is sin of x continuous? Is the product is x comma y goes to x times y a continuous function from R2 to R? It is.
Okay.
Um,
I guess you could use like a product rule sort of.
yeah, I mean, I suppose we haven't like literally proven that.
Yeah.
That's true.
That's what I was scared about.
Yeah, I mean, the thing is, at the start of this class, like, I didn't want to go through the let's do some elementary epsilon delta proofs. I wanted to save myself that day. Anywho, so this is continuous everywhere. So that gives me no constrictions on L, X, and Ly. So, scratch walk, this is continuous everywhere. So I see no constraints on Lx or Ly. M0 is the supremum of all of the outputs of f of x, y. That's one. It might be smaller if I have a smaller interval, a smaller rectangle, but it's only less than or equal to 1. M0 is less than or equal to 1. Louis, D2 of f needs to be less than or equal to M1. There exists some M1 such that D2 is less than or equal to M1. So, what do you get when you take the derivative of that function with respect to its second input?
Cosine of x times y times y prime.
So I'm taking the derivative with respect to the second variable?
It's just x.
Oh, yeah.
Yeah, notice y prime doesn't make sense right now.
I was
Y
thinking
isn't a function.
it wasn't differentiation. Yeah, that's x.
Neat. So it looks like cosine is bounded above by like 1, I guess. And remember, like it looks like I want x0 and y0 to be 0. And x is going to be somewhere between negative Lx and positive Lx. So what's an upper bound on x right there in absolute value?
Absolute value. Oh.
That's what I want to control. I want to know like what Lx and Ly should be. But there's no constraint there, right? That's fine. I guess I'll get a bigger choice for M1 if I let Lx grow. The fourth condition I need is I need Lx times M1 to be less than 1. I need that. So again, I can get some actual restrictions out of that. What's the upper bound I have on M1 right now? So this is something that I'll need. And right now I have Lx times M1 is less than or equal to Lx times Lx. So I would be happy if Lx times Lx were less than 1. Okay, so does that give me a constraint on what Lx is then allowed? Could Lx be 17? 17 squared is bigger than 1. So I think we want Lx to be less than 1. definitely is something that we will want if we want to appeal to the theorem. We also need Lx times m0 is less than or equal to Ly. Now it looks like we already want Lx to be less than 1. Do we have control over m0? It's less than or equal to 1, I think. So as long as Ly is at least 1, I'm happy. So it looks like I can make an appeal to this to show that there will be a unique solution on the closed interval from negative Ly to positive Lx to positive Lx for any Lx in 0, 1. And that's not like the proof, but you know how the proof is going to go now. Set everything so that you can make an appeal to the Picard-Lindelof theorem. And then once you've made the appeal to the Picard-Lindelof theorem, the conclusion is there exists a unique solution to the IPP. Cool. So, with like 7 minutes left, I think I want to go off on one tangent. So this says that there exist solutions to differential equations. Do you think that it gives you a way of figuring out what those solutions are?
Perhaps.
You need to find a fixed point of an operator.
You need to find a fixed point for a contraction mapping. Do you guys remember how the proof of the existence of fixed points for contraction mappings went?
Oh, yeah. You can do approximate solutions by computing a bunch of experimental recurrence relation.
So the unique fixed point of a contraction a contraction mapping is given by the limit as n goes to infinity, t applied n times to any initial function. So here's one way of approximating solutions to differential equations. Start with your favorite continuous function from, I don't know, I guess this says like 0, well, the open interval from 0, 1 to, I don't know, the closed interval from 0 to 1. That would do. How about the 0, how about, yeah, the 0 map. Yeah, that would do. There's an initial function. Then you could apply t to it, compute an integral, and get a new function. Then you could apply t to that and compute that integral and get a new function. And you do that like 1,000 times, you're probably pretty close to having a solution to that differential equation. Does that seem efficient to do?
No.
No, because you have to compute an integral. And I mean, computing integrals isn't that bad, approximately. But that means that at each stage, you're only doing something approximate, and those errors are going to propagate. So that's not the technique I would use if I wanted to approximate a solution to an IPD. Probably use Newton's method or Ricardo. Cool. So, I mean, that's all I have to say today. Maybe I'll tell you what we're going to do next time, on Friday. Do you guys remember what the implicit function theorem says? Do you guys remember the idea of implicit differentiation? If I give you an equation, I don't know. You can like compute the derivative of that equation by, I don't know, I guess you imagine that y is a function of x and then go from there. The implicit function theorem says if you start with an equation like that, then as long as some conditions about tangent lines line up, then there exists a function of x, so that y as a function of x solves that equation for every x. So So it says that you don't have to imagine that there's a function, that y is a function of x. Y is a function of x. And I guess like, I don't know, like, there's like one graph that you can get out of this, but is y actually a function of x there? No. So really it only says it locally. If you're only allowed to look in that little box, y is a function of x. But if you look in that little box, is y a function of x? No, there's a vertical tangent line, which is bad. If you look in that little box, is y a function of x? No. There's a point where you can't take tangents. But otherwise, if you look at any equation, you can write down y as a function of x. And the way that we'll prove that is by finding a contraction mapping whose limiting function solves the equation. Cool. So, I mean, I think that's good. I'm happy. I'm not good at ending. Oh, I should hit stop recording.